RC conference webinar series. Today, our guest speakers are from Extrel. I'll introduce Chuck DeCarlo. Extrel has been a very long time supporter of the conference, and Chuck has always played a major role in helping develop the content, and we sure appreciate your help, Chuck. And if you have questions, you can type those into the chat line, and at the end of the presentation, we'll ask those questions. With that, I'll turn it over to Chuck DeCarlo of Extrel to introduce your team and present the webinar. Thank you, Chuck.
Yeah, thank you, Steve. I appreciate the introduction, and just as we were saying earlier, excited for the conference coming up in August. It seems like that's approaching fast. So, joining me today, I've got Chris Williams. Chris is the head of our industrial applications group at Extrel, and since we were going to be talking about flare mass spectrometers, I was really glad that Chris agreed to join the conversation. He's got a lot of experience with our flare customers and going and visiting these sites hands-on. So, Chris, thanks for joining.
Yeah, glad to be here. Hopefully, I can share some insight from what our customers in the field are doing.
Yeah, and so just as Steve said, please, as we're going through talking about mass spectrometers, whatever questions you have, enter them in the chat window, and you'll have access to both Chris and I for some time at the end. We'll try to leave good time for discussion. So, okay, I should be sharing my screen now, I believe. Chris, can you see the presentation slides?
Yep.
Okay, excellent. Now I'm going to get started here. Okay, and today we're going to talk about flare gas mass spectrometers, and we're really going to try to be comprehensive. So we're going to try to cover as much as possible in the next hour, again, leaving time for some questions and discussion, but to try to get you really a complete picture of what is a flare gas mass spectrometer. So really, I've divided this into two sections, and we'll take two kind of different approaches to this. We'll start with, why are mass spectrometers used to measure flare gas? And we'll talk about, flare compliance. We'll talk about some of the challenges that are involved in analyzing flare gases, and we'll talk about why the mass spec is uniquely configured for going after that measurement. In the second track, we'll take a different approach, and we'll follow a sample kind of from the flare all the way through analysis, through data treatment and reporting, and we'll try to give you a complete picture of what it's like to incorporate a mass spec into a flare project. How are these things configured, installed, how are they used? So we've got a lot of stuff to cover, and we're going to be moving pretty quick, but send your questions in as they come up, and we'll try to make sure that we get all the information that's going to be especially helpful to you. Okay, so where do we begin? Of course, we want to start with the flare, which luckily for us, flares are really interesting things, right? They're fascinating for all kinds of reasons, not the least of which, right? The flare is an impressive object. You've got a tower that's over 100 feet tall, and it's got a gigantic flame shooting out of the top. Right. So for anyone who's had the opportunity to stand close to a flare when it's in operation, you can feel the heat, you can hear the rumbling sound, and it's kind of more than just interesting. It demands your attention. It's an impressive thing. Now, to add to that, what I find equally fascinating is that this giant flamethrower that you see in the middle of a chemical plant or a refinery is actually a safety device, right? The purpose of the flare is to destroy hazardous air pollutants, or HAPs, right? Compounds that are dangerous to people's health before they can be released from the manufacturing site into the air. So, what kind of things are we talking about when we say HAPs? Certainly in an oil refinery, for example, you've got a lot of hydrocarbons, right? That's a hydrocarbon manufacturing process. Likewise with an ethylene plant, other chemical plants. So hydrocarbons that can cause health effects to the local community. At oil refineries, it's very common to also have sulfurs. So H2S, COS, CS2, ethyl and methyl mercaptans can be in there. Different aromatics, including benzene, toluene, xylene. And then, depending on the process units that are upstream of that flare, you could have industrial acids, there could be ammonia, there could be chlorine compounds at chemical plants that use a lot of chlorinated compounds. And then mixed in with all that are air components, nitrogen purge gases, things like that. And all of these things can be vented out to the flare in various concentrations, depending upon what process units and what conditions the plant has to vent at any given time. So, a flare is a very dynamic object, right? It's not a fixed composition kind of a gas sample. Because the job of the flare is to destroy these things that can be dangerous to people in the surrounding area, the combustion at that flare is very important, right? And, when I say people are interested in looking at flares, it's not just because they're a giant flamethrower to stare at, but you can tell a lot by looking at a flare. For example, the picture of the flare that we have on the slide here, you see it's a big flame, but you don't see a lot of black smoke coming off of it. That's a good indication that you're getting good combustion. And good combustion is important for destroying the dangerous compounds. So the types of individuals who are interested in looking at flares, right, goes beyond people who are just interested in staring at the flames. Right? We've got the regulators also interested because it's the efficiency of the flare that matters for its safety. So if we look at this next picture of a flare, this is a different situation. Okay, so on the slide here, you can see it's nighttime, but the flare is so bright, it's kind of lit up most of the things surrounding it. The tower on this flare is 150 feet tall. And so if you kind of do some hand waving, you can see the flame that's shooting out of that is roughly 300 to 400 feet tall easily. So in this case, instead of a nice controlled flame, you've got a big out of control flame. And up above it, billowing out of the flame, you see big clouds of black smoke. Real signs that this is an uncontrolled flaring condition. And they're not getting complete destruction, which means hazardous air pollutants are being released into the atmosphere. And so here we see a great example of why the regulators care about the operation of industrial flares. They want to make sure that the owner of the flare is operating as safely as possible. And really, we'll talk a bit about the scope and the different types of regulations that are out there, but most of them fall into two main categories. And I've got a description of those categories here. And so the first category up at the top are rules that relate to the amount of sulfur containing compounds that are headed to the flare. Okay, so you can see this first group I've called out specifically H2S and total sulfur as measurements that are required. A really good example of this in the U.S. Is the EPA regulation documented under 40 CFR 60, so subpart JA. Sometimes people just call it subpart JA. And it requires that a refinery measure H2S in 0 to 300 ppm and total sulfur in a level that goes from ppm level up to high percent level. depending upon what potential exists at the site, for releasing that sulfur. So historically, if they had an 80 or 90% H2S release, they're going to have to measure total sulfur up to 80 or 90%. And that requirement really is based on the fact that if you combust sulfur-containing compounds in your flare, right, you're not going to destroy the sulfur. Instead, you're going to produce SO2, which is a major cause of acid rain, and some major environmental effects that result. So EPA requires that those sites are measuring the amount of sulfur that's going out of their flare. The other major class of regulations specifically relates to the combustion efficiency. And if they're running their flare correctly to destroy hydrocarbons, VOCs, these other HAPs that are in the vent gas. And the way that the EPA elected to do that in the US, and it seems like other regulators are following suit in other countries, is to look at the flow of the vent gas that's going to the flare during a flaring event, and then look at the heating value of that vent gas. And by measuring the heating value and knowing the flow, that site is able to demonstrate to the EPA, per the regulation, that they're maintaining at a combustion efficiency above 98%. So that's what the EPA wants. They want at least 98% destruction efficiency. And they've determined that if the vent gas heating value is above 270 BTU per scuff during that flaring event, the site has demonstrated that it's going to be destroyed by the flare. Okay, so a good example of this type of regulation is the recent update to MACT-CC, which is in the refinery sector rule. Sometimes people call this the RSR requirement, and it really all depends on combustion efficiency. So in addition to measuring heating value, right, to prove that you're above 270 BTU, those sites are also going to be measuring flow. They're going to be looking at smoke, evidence of a smoking flare. I'm not going to talk as much about those portions of the regulation because today we're going to try to cover so much specific to the analyzers, specific to mass spec, but it's all wrapped into those regulations, which are all about destruction efficiency. Okay, so I mentioned that the regulatory landscape, though, is more complex, right? There's a couple main categories of regulation, but there's many types of different rules that a refinery or chemical plant could find apply to their flare. So just to give some examples here, on the slide you can see that NSPS subpart JA that I just mentioned, right? That's a sulfur rule from the US EPA that applies to oil refineries. In Canada, specifically in Ontario, they've got also a requirement to measure those sulfur compounds, and rule 530/18. For rules that are focused on combustion efficiency, you've got the MACT-CC, the RSR that I just described, but the EPA has also put out versions of that rule that are nearly identical in detail, but in application they apply to ethylene plants, with the EMACT rule, or the MONMACT rule, which applies to other, polymer manufacturing and treatment sites associated with ethylene plants. Again, all looking at destruction efficiencies of their flares. Now, in addition to rules that could come from a federal authority, very often sites are subject to state and local regulations. For example, in Texas, there are HRVOC rules that apply to their flares. In this case, they require a speciated measurements. They measure specific VOCs, and they need to report the concentrations of those. There can also be consent decrees and other types of rules that are site specific. and flare specific. So any given flare, you could have several different rules that you have to comply with, and balancing that regulatory diversity is part of what goes into an effective flare plan. So things start to get complex as we move upstream from that flare. Okay, so we know that it's possible that any owner of a flare is going to be measuring several different things. What's available for them to go out there and do a gas analysis? As I said, I know that there's also flow measurements and the like, but today we're going to focus on the gas analysis portion. And here on this slide, you can see some of the examples of the technologies that get applied in flare gas. Starting on the left-hand side of the slide, a lot of sites will use sulfur analyzers. For example, this is the Atom Instruments FGA 1000. It's a total sulfur measurement device specifically for flare gas. It's made by Atom Instruments. And that will do a total sulfur measurement. Now, that's for the refineries and the people that have sulfur rules. For people that are looking to measure the heating value for the combustion efficiency rules, they've got some options for what they would pick to do a heating value measurement. One really good choice is a calorimeter. It's a device that's specifically designed to measure heating values of gas mixtures. And you can see on this slide, I've got a picture. This is the COSA Zentar 9610. And so that's going to directly combust a small portion of sample and get the heating value from that. Now, a lot of sites have taken another approach. They will measure the complete composition of the vent gas, and then they'll calculate parameters from the speciated, the complete individual composition of that vent gas sample. They can calculate parameters like total sulfur and net heating value, in addition to having, the actual speciated composition. And there are two technologies that get applied in predominantly in flare gas for that. So one I've got in the middle of the slide is the process gas chromatograph. And I apologize, I don't have a glitzy picture of a GC. I've got kind of a simple diagram there. My company doesn't sell GCs, so I don't have a good fancy picture of it, but it's a great technology. So we're going to mention that in there. The great thing about the GC is that because they've got the full composition measurement, that can be used for compliance with the sulfur reporting rules as well as compliance with the heating value reporting rules. The mass spec is the other technology that fits into that category. Just like the GC, the mass spec is doing a complete composition measurement when the user has the calculated parameters to comply with the rule, as well as the speciated analysis for use in other ways, which we'll talk about a little bit. Okay, so you've got the individual parameter measurements with the sulfur analyzer and the calorimeter, and then you've got the speciated approaches with the GC and the mass spec. And now we're going to get into the difference between the GC and the mass spec and how that applies to this measurement as well. Okay, so what is the difference? I mean, primarily the difference between the GC and the mass spec is the speed at which they're going to do the measurement. Both give a great total composition result, but the mass spec is going to do it much faster. It's going to measure that total composition in a matter of seconds, whereas the GC takes several minutes to do that analysis. Okay, and this has become particularly important in flare gas because of the way the regulation is structured. So, on this slide, we've got a diagram, and it shows kind of what a flare analysis system looks like from a total, kind of high level. And you've got in the middle of the slide your process unit that's dumping vent gas, down a line that's headed to the flare. Usually there's, a knockout drum right in front of the flare. And your gas analyzers, they're going to be, everything I mentioned is an extractive technique. So they're going to be taking a small amount of gas, out of that line, either before the drum, or I think most of the sites I've seen take it after the knockout drum. And that's going to be going back to an analyzer shelter, okay, where the analysis will take place. Okay. Now, in the rule, the requirement for heating value was based on a 15-minute reporting block. So the idea is that, if your gas analyzer is getting an update once every 15 minutes, you have enough data to be in compliance. You report that to the EPA, and you've done what you needed to do at the kind of the bare minimum. However, because the flare is not a static object, it is a device that has control points. There are ways to adjust the flare in scenarios where it's out of compliance, right? This is all about the efficiency of destruction. And if your flare is inefficient, if it's not destroying those compounds, you can improve its destruction efficiency by adding steam. And you can see here that on our flare setup here, they've got the ability to add steam. They open up these valves. Some flares, you can add it before the tip. You maybe also add it at the tip. It all depends on the design of the flare. We're not going to get into those complexities today. But in addition to adding steam, which increases the combustion of the vent gas, you can also add supplemental fuel gas. So usually in the form of natural gas. And this will increase the BTU value. So it'll increase the combustibility of the vent gas. And you can see that's valved, right into the line headed to the flare. So when the EPA set in a 15-minute reporting block as part of the requirement for the RSR rule and the EMACT and the MONMACT, what they did was they created something of a complex control challenge. Because if you had a flare and it was out of compliance, you've got the option to correct that by adding steam and adding supplemental gas and increasing the combustibility before having to report that as a non-compliant block. But in order to do that, you need to do a couple of things very quickly, right? Because within 15 minutes, you've got to be able to measure, apply your corrections, confirm that you are back in compliance, and then get that value to report now as a compliant 15-minute period as opposed to an out-of-compliant period. And so this has become the flare control challenge that comes into flare gas analysis. And this is the reason that the faster measurement technologies for heating value, so the calorimeter and the mass spec, have become a critical component for doing real-time flare control. Because you want to be able to measure, get your sample gas, do your measurement, report that data live to a flare control system that can then control the valves that are applying steam and control the valves that are applying supplemental gas. So, by maintaining kind of real-time control of that, not only does it increase the safety, right, of your compliance program, right, make sure that you're less likely to go out of compliance and have to report non-compliant conditions, but these flare control systems are very sophisticated. Many of them run on automated algorithms that kind of ensure peak performance from your flare, which also means that in the long run, you're saving money on steam and supplemental gas because you're applying the right amounts instead of over steaming or applying wasteful amounts of fuel gas. So there's some real advantages to having a good real-time control strategy. Okay, I mentioned that the mass spec does the measurement of the flare gas in seconds. So does a calorimeter. So this is one example that was an installation out in Washington State. You can see some data on this slide. It was a head-to-head comparison of a GC that they had installed on the flare next to the mass spec. So the two analyzers are in the same shelter. They're looking at the same gas. And you can see on the chart that over the course of 150 minutes or so, there's about 20 updates that they get from the GC, kind of spread out through that period, compared to the mass spec, which it's giving an update every 15 seconds. So 8 minutes with the GC, 15 seconds with the mass spec. Typically, calorimeters for this application can come in a couple of different configurations. The analysis speed for them is going to be anywhere from 5 to 30 seconds. But yeah, what you see in this example is not just maybe the amount of information that the control system has for making adjustments to the flare, but you can also see a lag in response in the GC curve compared to the mass spec curve, simply because that GC is taking 8 minutes to report each sample. So there's a lag as a result of the analysis time in its ability to recognize changes in the heating value of the sample. So the risk here, if you have an update point once every 8 minutes, and I've heard some flare GC companies talk about strategies to maybe reach 4 minutes per analysis. So that would be better. But yeah, the risk that you run when you're waiting minutes for that sample to clear, not only is that you have less chance of of control and confirming your correction before your 15-minute block has ended, but also you're not seeing that shift. You're not seeing the real-time change in your vent gas, which means that you're going to be chasing a control point with limited information, and it leads to difficulty in actually doing flare control, and that means reporting non-compliant results to the EPA. Okay, so now when we add flare control to the list of what parameters are required by the EPA, we now have kind of a more complete picture of the parameters that sites are considering when they're planning out their flare program and they're planning their analyzer strategy. So in addition to the kind of regulated parameters like BTU and H2S and total sulfur, sites are looking at what speed of analyzer do I need? Do I want real-time control on this flare? They also need to consider whether or not speciated results are important. So one of the wrinkles that came in producing the regulation was that a lot of flares see high levels of hydrogen, and the regulators were smart enough to recognize, or whoever was putting together the regulation was smart enough to recognize that hydrogen has a very low heating value, 274 BTUs per scuff. This is not an energetic molecule, but it is extremely combustible. And so if somebody owned a high hydrogen flare and the concentration of hydrogen went really high, it was going to put them right against that limit for being out of compliance. But they were still going to have a really combustible stream. So as a result, the regulators allow sites to apply an artificially high heating value to the hydrogen that's in that vent gas if the site has a speciated hydrogen value. So this has led to a lot of refineries and chemical plants wanting to have that speciated hydrogen number, whether that's from a GC or from a mass spec, because it ensures that they're going to have good high NHV values at times that they've got a lot of hydrogen. So there's one reason that they would want speciated hydrogen. The other big reason for requiring speciation is if the site is under something like an HRVOC rule where they're just required to report their VOC concentrations. So, those sites, it's always going to make more sense to put on a full composition monitor than going simply with, a BTU analyzer alone. Last thing that a lot of sites need to consider is the nature of regulations, over the years that we've been working in flare gas, we have seen new rules come up. We've seen new agreements take place on a site. We've even seen, I'm talking to one of our flare customers right now, they're changing their process, which means new gases to their flare, which means that flare's under new updated requirements. So one of the things that was important for a lot of flare operators to consider was, are the analyzers that they put on here going to be future-proof for the next iteration of flare regulations that they're going to have to deal with? So that was an important consideration as well, which is flexibility. Okay, so when we add together that list of challenges, we come up with why a lot of sites saw the advantages of the mass spectrometer. So flare gas mass spectrometers, they measure everything, right? They measure the BTU number. They can do it fast, 15 seconds per update for that real-time control. They also have the full speciated composition for HRVOC, for example, or for either the speciated hydrogen for doing the elevated NHV reporting. Typically the analysis time is anywhere from 0.1 seconds to 0.4 seconds per component, so very fast. And the mass spec's very well suited to flare samples because, unlike GC, where you pick fixed analysis ranges, from PPC, ppm to 1% or ppm to 10%. On the mass spec, the analysis range for all components is always ppm level to 100%. And so when we've got a sample like a flare where these concentrations can change in a very dynamic way, the mass spec can follow them without any special hardware or ever having to change hardware because something goes out of range. It can track concentrations for anything up to 100%. Lastly, the systems don't utilize any carrier or detector gases, so they're light on using those. They're light on using utilities, which is good, and they're flexible. So just as the columns and the detection ranges aren't configured specific to a flare gas mass spec, the analysis method isn't set in stone either. So components can easily be added. It's done in the software, and the hardware never changes as a result of which compounds they want to measure within that sample. So sometimes we will configure the sample path for the sulfurs, for example, but we'll get into those details in just a little bit. Okay, so how is it that the mass spec does the measurement, and why does it do it so quickly? So the big difference between the mass spec and the GC comes down to how they're separating the sample in order to do the analysis. On a GC, that sample is moving through a chemically active column, and you're getting physical separation of those molecules before they're being detected, it's a great approach for getting nice discrete samples, but it takes time to physically separate. Alternatively, the mass spec takes all of that sample into a vacuum chamber all at the same time. It ionizes it and then scans it electronically. The result is that each molecule, when it reaches the detector, produces a unique fingerprint, which is called the mass spectrum. That's why it's a mass spectrometer. And here you can see the mass spectrum for methane, a really common flare gas component. And it gets this distinct pattern of peaks that appear that are a result of the methane molecule's ionization. Now, each component then has a different set of peaks and a different pattern. So ethane is different than methane, propane is different than ethane, and that's how the mass spec tells all of these things apart, even though it's scanning them simultaneously. So this slide actually shows a cutaway of the mass spectrometer that is used by Extrel. It's something that's called a quadrupole technology. quadrupole mass spectrometer. And the reason for that is that in the middle of the vacuum chamber that I mentioned, right, there is an assembly with 4 parallel rods. That is the quadrupole. So I said that all of the gas is entering the chamber at the same time, right? We are ionizing it. It's then the quadrupole that is separating those ions and allowing the detector to see how much ethane is there, how much methane, how much propane, how much hydrogen sulfide. It's a great technique because there's no class of compound that it can't see, so it can do the hydrocarbons and the sulfurs. It can look at the air components. It can look at unusual compounds. Some chemical plants, have, chlorines or alcohols. All those things can be detected with a mass spectrometer. Okay. So if we want to tie all this together, right? What does it look like to do real-time flare control? Luckily, we've got a video that we can see a pretty good example. And if you remember, this is our flare from earlier, right? This is our flare that had the problem. It's got, a 400-foot tall flame sticking out of the top of it, and all this smoke, out of control flame. This actually was a flaring event that occurred back in February of 2018. And this is a refinery. It's in the Midwest, and they had an emergency shutdown of the diesel hydrotreater. So what we're looking at is a mixture of diesel fuel and hydrogen that's being sent out to flare, and that's why they've got this kind of out of control condition. Okay, but as it's being as we're watching the film now, look, you can see the flame starts to change shape. Now what's happening is this site had a mass spec doing the vent gas analysis, and it had a program that did flare control that was taking that data along with the flow data, and it's doing an automated control of the steam and the fuel gas application to bring that flare back in line. Now you can see that we've got a nice controlled flame. The black smoke is actually replaced here by steam. So you can still see some stuff coming off of it. That's steam. That's because this was in Ohio in February. So, it's freezing outside. And there, really, in less than 60 seconds, they went from, a flare that was completely out of control to a flare that is operating at, peak performance, destroying all the hazardous compounds. And actually, in this case, when the EPA came knocking, 2 days later, which they did, the site was able to sit down and demonstrate that, here's what happened, here's what our flows were, here's what our vent gas heating value was. Our combustion efficiency never went below 98%, and this was, a totally compliant event. So it worked out really well. One of the things I think that is interesting about this event is that the video was posted to YouTube. So it was actually filmed by someone living next door to the refinery, and so it just underscored the degree to which flares are subject to a lot of public scrutiny, and so important for all of us in the industry to want to operate them at peak efficiency. Okay, so that was kind of a quick introduction, but I think we were able to cover, what is that flare gas mass spec and why is it being used, on the flares, right? We talked about the fact the mass spec is a single analyzer for measuring everything within that stream and for covering all of the required parameters. So BTU, total sulfur, H2S, you get flare control in real time as well as the full speciated analysis. Basically, nothing's going to measure as much in the sample or do it as fast as the mass spec. And then lastly, we talked about future proofing because the mass spec can see all types of components, and because it doesn't require hardware changes to kind of reconfig. It's very flexible for dealing with changes in any future regulations. Chris, I know you were working recently with a customer on updating their flare program. Could you describe that process a little bit?
Yeah, I was working with a customer out in West Texas. They had originally purchased the mass spectrometer to do their sulfur analysis, the H2S and the total sulfur measurements required under JA. Their extended deadline recently came due for them to come into compliance on their 4 flares for the BT or heating value measurement. They reached out to me. They were interested in hearing what all would be required to bring the analyzer into compliance, what updates they would need to make. And so I got some information back from them, about their current software configuration and their current analysis setup, and took a look. Identified some additional compounds that they would need to measure, and had some discussions with them about that. And then we also talked about the additional standards that would be required for their quality checks. And then I gave that information to our technical support team, who was, already scheduled out to do a preventative maintenance trip within the next couple months. They were able to make the updates for them, and the only work that was really required to update the analyzer for that new regulation then was a few software changes and a few additional, gas standards to be purchased.
Okay. Yeah, thanks. I appreciate you mentioning also the gas standards, because I'm going to talk a little bit about gas standards for RSR and for validation. So we'll get to that here. We want to transition now, right? So we've talked about why are mass spectrometers used in flare gas? Okay. Now, what does it look like to incorporate a mass spec into one of these projects? What does it look like to use and operate and calibrate a flare gas mass spec? Okay, once again, where do we start? We want to start with the flare. Okay, so this is our diagram from before, right? It shows kind of the entire setup, right, for our flare gas analysis and control. And we've got, the gas coming from process, coming from upstream, and the vent gas going out to the flare. So all of the techniques that I mentioned, certainly the mass spec, is an extractive technique. So we're going to have a sample line, right? And that's going to be pulling gas back to, the sample house, the analyzer shelter, which, typically it's not going to be right at the base of the flare. There's all kinds of reasons for that. But they're usually fairly close. This umbilical is often heated. I mean, you can see the measurement. In this example, the probe is after the knockout drum, so there's usually a fair amount of water in there. I don't know, Chris, would you say somewhere 1 to 3% is like standard in our flare samples that we see?
Yeah, in my experience, it's usually about 1 to 3% by volume under most conditions. When they steam some of the lines to clear them out, the concentration can go up, but 1 to 3% is typical. Yeah,
okay, that's a good point about the steaming. The mass spec itself can measure those steam concentrations. It's not a problem for the mass spec to analyze steam, but we do want to make sure it doesn't condense in your sample lines. So heated sample lines. And then after analysis, right, the mass spec's got to be sending data out into the flare control system that I mentioned, that then allows it to make the corrections that it has to make. Okay, so let's talk about how does the mass spec, incorporate into this setup. Okay, a note on the sample system itself. A flare sample system's pretty standard. Generally, you've got that heated umbilical that we mentioned. Typically, there's a pump because the flare gas usually maybe a little above ambient, maybe it's at ambient pressure. And that pump is going to be delivering it back to a cabinet that's filtering it. And again, it's going to be a heated cabinet to prevent condensation in the sample system. And that's really what we got here. So on the diagram, we've got the sample coming in. In this example, there's a couple of different sample lines. Usually flare analyzers are dedicated to one sample, but occasionally we might see a if it's practical, we might see an analyzer connected to 2 flares or 3. And some small amount of samples, there's going to be a fast loop right at the sample cabinet, and then some small amount of sample is going to go to the mass spec itself. So once we get into this gray box, we're talking about the inside of the mass spec. And really 100 cc's a minute of sample is sufficient for our analyzer. And in fact, when it does its analysis, it's really only using 10 microliters per minute. So only a very, very small amount of that sample ever goes into the mass spec itself. It's important because the analysis is happening under vacuum, but it's also really good for protecting the mass spec internally from anything like corrosive, like HF acids, or from sulfurs from H2S. The rest of that sample, the vast majority of that 100 cc's per minute, can then loop back out to the flare. Sample condition requirements pretty typical in this application for a gas analyzer. We want it to be free of particulates. We want it to be free of condensing compounds. On this slide, we can see actually a picture of the inside of that sample selector box. And what you see here is, first off, it's heated. So we configure our sample selector for these applications typically to be above 125 C. Make sure we don't have any cold spots as part of the analyzer's installation. And we've got in this unit, you can see this is the sample selector box here on the side of the system. It's kind of the picture in the middle is it blown out. And this component here is a multi-port sample selector. Those ports are usually connected certainly to the flare, or if it's used, looking at more than one flare, to multiple flares. And then additional positions will be plumbed to calibration bottles. So the calibration bottles, if they're permanently plumbed, they're ready for doing any kind of automated measurements or any kind of scheduled measurement that's required for the flare application. So we'll get into that a little bit. Most systems have one of these units, which gives them 16 sample ports. Sometimes if the site is looking at significantly more, they might have a 31 port config, which would be 2 of those selector heads. In addition to managing condensation, the sample path also has to be designed to deal with anything like surface interaction from H2S sticking to the stainless steel. We do that by coating everything through the entire sample path with sulfur inert coating. So that's a very commonly used standard option for flare mass spectrometers. And at sites that have, HF alkylation upstream of the unit, there could be aqueous HF acid, coming down the line. Even in trace levels, that can be very corrosive on stainless steel. And in those circumstances, we configure the systems with the Hastelloy C sample path that stands up to that acid. The chart here just simply shows an example of, the kind of H2S response that we see on the analyzer. This was a run that we did at a gas manufacturing site just outside of Houston, and we took 100% H2S and we ran that through our Hastelloy coated sample selector and analyzer, and we wanted to see how long it would take to get under to that 300 ppm threshold. And we actually hit that mark before we got out to 10 seconds. So actually, I think we hit that somewhere after 5 seconds. So very, very fast response when we got the sulfur inert coating. Okay, now, when we're working with our customers to put together their measurement, it's going to be critical for us to understand what kind of components they want to measure. And this is determined by what regulations they fall under, and it's also determined by what process units are upstream of the analyzer. So you can see here, this is a fairly complex example of a flare application where the column on the left-hand side shows hydrogen, it shows air components, many hydrocarbons, and several sulfurs. And what our engineers do is they take this, they design the analysis method, which tells them 2 things. One, out here you can see on the on the right-hand side of the slide, it's going to tell us exactly what kind of performance they can expect for each of these components at these given concentrations. So you can see, plus or minus 200 ppm, in the nitrogen component here, plus or minus, 0.1%, 1,000 ppm. We want to make sure that we understand exactly what performance the mass spec is going to get on that flare, prior to ever doing the installation. It helps the flare program be developed properly to know that they're going to be measuring everything they need and getting a good response. It also tells our engineers what calibration gases are going to be required in order to do that measurement. Okay, so here you can see an example of what we call interference. So within the mass spec, we said that it's taking all of those components at once and it's scanning them electronically. When it does that, sometimes there are components that have similarities in their mass spectrum that need to be accounted for prior to reporting the data. By designing the method appropriately, we ensure that the mass spec has all the information it needs to separate any component interferences. For example, this shows a mixture of nitrogen and CO2, just to show how their individual mass spectra would stack up for the mass spec. Well, in the course of doing its measurement, the properly designed method will remove that interference and make sure that it's reporting just the concentration of nitrogen and CO2, and the user never has to worry about separating those two manually. It's all done in real time automatically by the software. To do that, we require calibration gases. The mass spec, it does use more calibration gases than the standard GC that would be applied in a flare gas installation. There's 3 types of mass spec cal gases that are used. 2 of them are pretty much identical to the kind of cal gases that you see for the GC. That's the background gas, which is used to take a 0 value, kind of zero the analyzer, and the sensitivity calibration. This is very comparable to a GC span gas. This is the gas that allows the mass spec to adjust signal level to concentration. The reason the mass spec has more cal gases than the GC is this 3rd category, which are called fragment calibrations. The fragment calibrations are what give the mass spec the information it needs to do those interferences and separate them in real time. So by adding those extra calibration gases, we enable the speed of the mass spectrometer. So this is really why the mass spec is able to measure all the things that it measures and still report them as quickly as they do, and report them in seconds. While the mass spec uses more calibration gases than a GC would in the application, one of the nice things is the mass spec itself consumes very little of the calibration gas. So, it's very common for an installation to, instead of using like the tall cylinders, that are like about 4 feet tall, for these fragment calibration gases especially, gases that are only used, once or twice per year, just a couple hundred cc's, used in the course of the year, they might get the small bottles and put them in a rack, kind of conserve space on the side of the shelter. So mass spec will use more standards, but it uses very little gas. Now, important to the flare application is the process of validating, doing quality checks to make sure that the analyzer is accurate. This is written into most of the regulations. So for all the regulations that I mentioned previously, we've got users who have written into their flare program and designed the mass spec to do a validation. That's to go out and check a validation standard and conform to the requirements of the rule, whether it's a subpart JA rule or whether it's RSR. So those gases, we kind of think of those as being our validation gases as opposed to our cal gases. And it's common for the rule to require a check of a validation gas by the mass spectrometer either daily or quarterly or annually. So there's a schedule that will be written into the rule, and we can help users navigate that world and help them think about how they want to plan out their daily checks and their quarterly checks. On this slide, you can see examples of the gas blends that are used at most flare sites in the U.S., most refinery flares in the U.S. for doing the net heating value cal checks, the low, the mid, the high. So we can get people details on what kind of blends they might design to make those validations as easy to maintain in their program as possible. Last thing I'll comment quickly on with regard to validation, for the sulfur rules, a lot of folks were required to do validations based on their historic highest level of H2S present in the flare, and actually to validate on a standard that was like 120% of the historical maximum. For a lot of sites, that meant high percent H2S gas, at some of these refineries. That's a really dangerous gas bottle to have on hand. For those sites specifically, we developed an application that they can put into the Air Monitoring Authority to apply for an alternative monitoring plan or an AMP that would allow them to do those validations using, instead of high percent level H2S standards, using ppm level standards only. So I really urge anyone who's stuck doing daily validations with high percent H2S, apply for an AMP based on the increasing the safety of the setup, and go for the ppm standards instead. Okay, now beyond calibration gases, the utility requirements of the mass spec are extremely low. It requires power and purge gas. Most of these systems are all class 1 div 2, and so that would be required. No carrier gas or calibration gas is required for the installation, so very simple in that regard. Data reporting, of course, all the standard data protocols are available, and that ensures that the site has the data that they need to keep their program in compliance. Last thing I was going to comment on is just maintenance procedures. I know I'm up at the end of the hour here. The maintenance on the mass spec, very straightforward. And actually on this slide, you can see all of the standard maintenance procedures that are required by the flare analyzer. So the flare mass spec, you can see here, it is designed on a movable stage. So that the front panel of the system is really a door that can be opened, and the mass spec actually can slide out, so it's easy to work on. And the biggest maintenance component is to change the oil in this pump twice per year. That's the manufacturer's recommendation. Once per year, we recommend that a flare customer do internal maintenance, and that would be taking out this component here. It's called an ionizer. It's mounted to really the inlet flange, which is on the side of the vacuum chamber, and that's a very easy component to replace. It just pops off, they pop a new one on, and at that time we also recommend that they go in and clean their quadrupole. So it's easy to do. I typically, when I started in service, when I clean them, I would use a toothbrush and a detergent that we supply with the analyzer. It's basically just Alkanox and some pumice. For emergency procedures, the number one biggest risk that the systems tend to see is if there's a problem in the sample system and condensates are sent to the analyzer. If somebody sends liquids down to the analyzer, that's the biggest emergency maintenance situation. And in that case, this component here in the middle of the slide, that's the inlet, this might become plugged. There's a good and bad to that. The bad thing is you're no longer getting your gas in to analyze, but the good thing is that plug protects the internals of the system from anything that was in that liquid. So greases in the hydrocarbons or acids, like one of those HF sites. That's all taken by the inlet, not by the mass spec itself. And then there are filters in that sample selector as well. Those are there to help protect against particulates and moisture. And if there's a breakthrough, those need to be replaced. Now, for doing that maintenance and for, doing, check-ins and the like, in addition to, your on-site staff, a lot of refineries and chemical plants will utilize service from the vendor, and there are service contracts available. So in flare gas, we see it's very common for those sites to get a service contract and have us send technicians to do the maintenance on the systems and do calibrations, twice per year for platinum contract, maybe once per year for a lower tiered contract. So yeah, we see a split in flare gas between those who like to do all the service themselves with their staff on hand and those that like to utilize the service contracts. But either way, in a compliance program, of course, uptime is essential. So long maintenance intervals and ease of service is really essential. So, okay. I appreciate everyone, joining us. In conclusion, there's a lot to cover there. First kind of talking about why the mass spec is uniquely suited to a flare program where they need to measure a lot of things. They need to measure them quickly if they want to do control, and they want to have flexibility in case the regulations change and they need to update. And then lastly, how do they use the equipment? They want to make sure that they have a system that is easy to integrate, right? That it's easy to maintain, and that provides the data and control of the system in an automated and usable package. And so in a very fast, high level kind of a way, that's the introduction to flare gas mass spectrometers. I know we're just over time a bit, so I appreciate everybody's patience sticking with us. I can stay on for questions. I don't know if Chris can.
Yeah, I'm still available.
I have several questions, but I'd let others go first.
No, Tim, the floor is all yours.
Okay, nobody else has any questions?
They'll wait.
Okay, so how many calibration gases do you guys typically see in flare applications for the what you call the fragment calibrations, or for the interferences? How many do you typically see in an oil refinery?
Yeah. So, and Chris, you can chime in. As you've been to a lot of those sites as well. But I would say typically it's between 4 and 10.
Okay.
Yeah, those would be the numbers required for compliance. Some of our customers have process engineers interested in more information, speciating, especially some of the heavier hydrocarbons. In those cases, we might need, closer to that 10 range or maybe even more if they're getting additional information beyond the minimum for compliance.
Okay.
Yeah, I think. Sorry. I was just going to say, I think, just exactly as Chris was saying, the key to that, that number gets determined by the level of speciation that the site wants to see.
Yeah. Okay. As far as it, the one thing we, of course, have an estimate for our flare composition, which is just an estimate. So let's say we hook one of these things up and we start running it, and we're seeing some things that we're not expecting, which could be, pretty much anything in a refinery, or maybe even small additives that we use here and there. How do you work that out? Do you guys have like a master database of various compounds that you can? Is it called like a fingerprint?
Yeah, mass spectrum fingerprint's a great way to describe it.
Do you guys have like a database where you can kind of figure out what those are in the event there's some unknown compounds?
Yeah, Chris, you were just working with a customer I know, kind of optimizing their approach. You just mentioned it to me. Do you want to kind of describe what that scenario has been like?
Yeah, I actually find this topic really interesting. It's a lot of what I continue to do with our flare customers. Yeah, so like you said, a lot of customers have an initial idea of what's in the flare. They might have some data that they've collected from lab samples or such, but they know, like you said, that the flare can have anything in it, right? Anything from the refinery or additives that you might use, like amine scavengers and such.
Yep.
What we've done in many cases is, in addition to the scan that they would use for compliance, that quick 15-second scan that Chuck was mentioning, we can do a broader scan that's run periodically and look at many of those peaks of interest that might be used by scavengers or other sulfur compounds, heavier hydrocarbons, aromatic compounds. And then during flaring events, oftentimes engineers are interested in what's present during the flaring events, or even under normal conditions. We can go back and look at that historical data. And then, as you mentioned, there are actually many databases available with a lot of mass spectral information, or those fingerprints. We have some of that in our software readily available. A lot of the more common hydrocarbons and other constituents are already programmed in our software, so that data is accessible by the user. But also the US government, the NIST agency, has a very complex and large library of these mass spectra that we have access to, and actually many people have access to through Google. So we can, compare what we see in those larger, more diagnostic scans against those various databases, as well as our experience looking into that stuff with, existing flare customers, and update the analysis method, or at least give, the engineers an idea of what was present during a particular event or at a particular time.
Okay. So I guess I'm kind of thinking this through. If you would, I mean, how is that presented? I guess, is that on the local interface? Because I mean, if you were, you'd have to detect it and then configure it, I guess, on an output if you wanted to measure it. But I guess it would be displayed locally, and then you'd have to configure any of these new compounds to be reported on your output system.
Yeah, no, that's exactly right. And I think you've probably got the template in mind. These systems are going to be connected typically to a DAS and a DCS, and what is being reported and the format in which it's being reported is specific to that flare. So that's part of the standard commissioning, is to work with the user, and a lot of times we're working with maybe an environmental reporting company, that's helping out with that aspect of it. But the other data, right, everything that's measured is, recorded and viewable on the mass spec. So if somebody wants to do application development work, or they want to see something, for the engineers, as Chris said, they can do that right on the terminal computer that's running the system.
Okay. Is there can you log in remotely and see those types of analysis?
Yes. Yeah. So all of the control software for the mass spec is built, to allow for different levels of login access. And so, sites that want to take advantage of that, they can set it up so that any computer with the proper network security settings can access the mass spec and, log in, look at data, look at instrument status. We've got people that will check it from home, like if they don't want to go on a call out in the middle of the night, that kind of thing. The other way it could get utilized, especially over the last year, is we can create access channels so that, our support people can log in. And I know, Chris, this is something that you do, right, fairly often. I don't know, how often do you think you will log into a customer's system?
I mean, it depends. I usually log in a few times a month to various customer systems when, their site IT policies allow. In particular, this past week, I probably did 4 or 5 logins. There's been a lot of interest in updating applications recently.
Mm-hmm. Yeah, that's the only drawback is on our side is the security. We've got to keep, completely separate networks. So we'll have to see what that looks like if that's something we want to do.
Yeah. I mean, the whole software is based on the whatever the government security standards, like 21 CFR Part 11. There's regulations for and so for those sites that have those kind of IT requirements, of course it applies to all of that, and we don't need to be able to log in. But if people want to take advantage of that, so that their I&E people could check on the systems, from across the plant or from their home, it's there.
Yes. Yeah. Yeah, we've done a couple radio type signals in the past where it's completely separate. So maybe they can get to the analyzer, but they can't get to the rest of the network. So that might be a possibility. So service techs, what is so you're in Pittsburgh, right? I assume your service is based kind of out of Pittsburgh. Is there technicians across the country, or give me an idea what that looks like?
Yeah, no, that's a great question. Yeah, so our service is really, it's spread regionally. Our factory is in Pittsburgh, but we've got individuals in Washington State, I think South Dakota, Texas, Alabama. I start to lose track of where they are all located, and in Pittsburgh also. But yeah, those are dedicated service techs, not sales/service, and that's Extrel service.
Do you know how many techs you have in number in the States, approximately?
In the U.S., is it 9 people in the department now?
Yeah, I think we just brought on a 9th, and the team's expanding as the number of installations and contracts goes up.
Sure. Okay. Do you find that with some training that these can be managed by the site after they've been trained?
Yeah,
absolutely. Our service team offers, with COVID, it was a little bit different, but our service team offers training courses in Pittsburgh every couple months, and we're going to be doing training courses down in Houston soon, hosted at Cosazenta, our sister company. We also do site visits to, do training. If you have a larger group of technicians at your plant and you can't travel, we offer site trainings as well. And the maintenance is pretty easy to learn. All the main maintenance items, we usually take about 2 days to go through the entire procedure and teach about troubleshooting and calibrating. So a lot of our customers have elected to maintain the instruments themselves. The analyzer is kind of designed with a serviceability in mind.
Yeah, I think we did we checked earlier in the year, I guess, to get the kind of update on it, but we've got about a 50-50 split with our industrial customers in the U.S. for those that elect to do the service themselves and those that opt for a contract at one level or another.
Okay. Yeah, we've got GCs right now, and there's a couple areas that are quite difficult to work on, especially if you have big hands. It's hard to just get in there. And then, the heat tends to cause galling. Are there any special tools required for the analyzer repairs?
If I'm thinking about my toolbox, I'm usually dealing in wrenches and digital multimeters, some Allen keys and screwdrivers. Like Chuck mentioned, like the cleaning, we're using toothbrushes and Q-tips. So there's not really any specialized tools that are required.
Okay.
Yeah, I mean, yeah, I guess really beyond the, a multimeter, everything's just little hand tools, screwdrivers.
Oh yeah,
Ouch.
we've got all the common tools, but in some cases for GCs, you need a special tool to hold the furnace tube so it doesn't break, or you need a tubing fitting feeler gauge so you don't over tighten the tubing. There's a host of little special expensive tools that are required. So I'm just trying to cover our bases on this.
Yeah. I mean, the great thing is if you have techs that are used to working on GCs, then a mass spec is something that's really quick for them to learn. And as far as the difference between the two, usually it comes down to, I mean, GC is a great technology, but they require more check-in, right? More retuning typically than a flare mass spec will. One of the reasons we like to advocate that people send their staff to Pittsburgh for training as opposed to doing on-site training classes, is that it's a compliance device. So you really don't want to take it offline and rip it apart. Whereas if they come to Pittsburgh, we got a couple analyzers that are just trainers, and so they can take it completely apart and they can see everything and do that a couple times.
So we actually have one of these things that's never been used because of a shift in economics. It's pretty old. It's like 8-10 years old. Has it changed very much from to do a flare, we would have to go to the silk inert and possibly the Hastelloy. This one was just for fuel gas analysis. Has the design changed very much from, say, 8 years ago? Is that something we could go look at and kind of train on?
In terms of advancements over that time period, and the biggest ones are in terms of electronics and computers. So if you were training on the physical layout of the hardware or the pumping systems, it would be very similar.
Okay, cool.
And in fact, Chuck mentioned our trainer units in Pittsburgh. I'm pretty sure 2 of the trainer units we have are that old model. Well, the old computer would be identical to what you would have on your system. So
yeah,
certainly we have tons of those. That would be the Max 300 IG product. We have a lot of those still in the field, and we still regularly train customers on that slightly different design of the enclosure.
Okay. I was just curious. My boss just asked me to ask about spares and spare availability, especially if it's silk inerted or Hastelloy. What does that look like? Is that something you guys keep on the shelf? If I bought an analyzer that's silk inerted and Hastelloy, how many spare parts does that entail typically up front?
Yeah, so I mean, we maintain a spare stock continually to kind of serve that marketplace.
Okay.
And by virtue of the installation base that we have in flare, for us, the Hastelloy C components and the sulfur inert coated components, it's standard parts, and it's built into our our spares stock program. So we do have users that like to buy and maintain some, have a couple spare inlets laying around just in case they take a slug of water and they want to, pop one in. But, in the US, we overnight parts all the time, if somebody needs something.
Okay.
And the sulfur inert things, the Hastelloy C things, that they're no different for us in terms of spares replacement than a stainless steel inlet would be.
Okay. Yeah, we normally keep common spares, and it is regulated to 5% or less per half for downtime. So we would certainly have the common spare parts on our shelf. So
Yeah. Yeah, I mean, our contract customers, we look at the numbers, they maintain an uptime greater than 99% in these applications. Certainly, availability of on-site spares helps add confidence to that.
oh yeah,
Undoubtedly.
yeah. My plant manager would give you a hug if you got 99%. Has not been very reliable. So,
Hey, Chuck, what percent of the facilities are using their automated control systems versus having the operator still override? And I just asked the question. I know in the last 2 weeks, 2 different facilities that basically the operator still, if they see 30 seconds of smoke, they crank up steam. Well, that's exactly what you had before. So that's not any different than what we had 5 years ago. And we spent hundreds of millions of dollars on all of these systems. How, one, you have a feel for how many of those systems out there using GCs are actually using the automated control system versus whenever there's any smoke, they're still steaming?
Yeah, that's a great question. I've got a pretty good feel for how many of the mass spec customers will have not just not just confidence in their control system, but even I got an idea for how many of them are feeding a automatic flare control program. Like the example video in the presentation, right? That was us sending that signal to a program specifically designed by one of the other 4Cs vendors for doing automated flare control, and you could see the result was really fast. But yeah,
That's the Flare IQ.
yeah.
Yes.
But we do have some of our users, they'll use the mass spec and they'll do manual control. And I think that they're comfortable with that, so that's what they continue. We do get approached still now by refineries that they're technically compliant, but they can't control. So that's why they're looking at a mass spec now. I mean, the GC that they have, for example, gives them the 15-minute updates. So they've been compliant since RSR. They've been able to report adequately since RSR came into place, but they haven't been able to control. And so that's what has us talking to a lot of refineries to this day, as they're kind of upgrading.
Yes. And as you know, I'm a big advocate for the combination of the mass spec and the Flare IQ, in part because what you saw there is when people put those two systems together, the control will actually work, and the operators will trust it over time. Whereas a lot of the other arrangements, the operators aren't getting a trust for those systems, and therefore they may or may not be using them sort of times that we would have envisioned them, envisioned the use of the data.
Yeah, and you get old habits and manual oversteaming, and yeah.
All right. I just didn't know from customer interaction that you're still getting feedback from folks that have GCs where they're saying they're not getting the control they want and need. So now they're still moving towards my spec.
Yeah. I mean, we've seen the marketplace change over the last few years. The regulations moved on to, the regulators in the U.S. moved on to look at the chemical industry and ethylene plants and some of the downstream polymer sites. And now we're doing a lot of work overseas in Korea, Taiwan, and Canada. As Ontario's put in the sulfur rule, but we're still talking to refineries. And we're still talking to refineries don't want to do JA work, and they want to do RSR and get a flare under control.
Yeah, we've had mixed results. We've had to pretty much lock our system in auto because everybody wants to throw steam to it. And one of the other thing, I'm not sure if it was, I think it was Valero Corporate. When you start into a flaring event, it's usually, because we have flare gas recovery, it usually pops up pretty quick, and then it'll slowly taper off. And what I kept trying to explain to everybody is you can't use the steam flow measurements below a certain number because it's such a large span. You can't say I'm measuring 70,000 pounds an hour of steam if that's your span and you're measuring 500 pounds. It just, the meter is not going to accurately measure that. But then you start running this through this net heating value calculation, and you end up out of compliance because the numbers are meaningless. So they finally, I think, have thrown out the last 15-minute sector or whatever they call that slice. I think partly because of me trying to explain that to them, they just didn't understand it. It's garbage in, garbage out kind of thing. So kind of like what you're saying is,
There are meters with much higher turn down ratio, which is part of some of the solution out there also. I don't know, are you using the old weir type or old type meters, or are they new
they
meters?
are so we already had orifice plates in our flare. So what we did is we used the Rosemont conditioning orifice plate with the mass flow transmitter, which has pressure, temperature, and differential inputs. And, based on their analysis, I think it's 22-to-1 turn down, which met the 5% just barely that the government specified for the project. And we've had pretty good luck. We had one, the flares are typically at one end of the plant or the other, and in our case, somewhat remote for safety reasons. And we've had one problem with one orifice plate tending to plug up with, we think, scale. So we have to go down and pump it about every 3 weeks to 4 weeks and just, make sure the taps are clear. But other than that, you're asking, what I always say is you're trying to control the uncontrolled. It's not like a heater where your conditions are the same day in and day out. When you have a flaring event, depends on what unit's involved, depends on how big it is. So it's actually surprising how well we've done considering those factors. We've learned now we've been in compliance to a high degree in the last, I don't know, 9 months or so. So, but there was a learning curve, like you were saying, because guys want to, the flare smoking, so they want to throw a bunch of steam at it, and you can't do that because then it drives your net heating value out of compliance. So, it's hard to train when you're controlling something that's abnormal. So, but I think we've got a better handle on it now.
Yeah, that's always the challenge with the controlling a flare is always a challenge. You've got all different, the turn down ratio issues, the timing of the results.
Oh yeah.
Flow composition. And of course, there's always the operator. The operators don't want to see smoke.
No, we're right on the highway right outside of Memphis, so a lot of exposure. In fact, I don't know if you heard about that bridge that cracked in Memphis, that has I-40 shut down over the Mississippi. We're, like a mile or so. Wait, excuse me, about 4 miles from that. So all the traffic backs up right in front of our plant. So lots of exposure there. So you can't blame them,
That's got to make it fun getting to work.
Well, it backs up in the afternoon, so it doesn't hurt us coming in the morning. In the afternoon, I go the other way. Now, some people that live over the bridge are, it's just a mess for them.